senior CPPC seminar today. Today we have a speaker from IPMU, Yun-Tsung Lai. He's gonna talk about the real three-body B decays at Belle, and he will also we also have a measurement plots, measurement results that haven't been published yet. Yeah. So, Yun-Tsung, floor is yours.
Okay, thank you for the introduction and invitation. This is Yun-Tsung Lai from University of Tokyo, KEKB IPMU. So the topic today is the study of the Charmless three-body B decays at Belle. And this is a brief introduction about why we are interested in such kind of the decay. So first, this is Charmless decay, so it is suppressed in the state model. And usually it is sensitive to the new phases if we consider the possible contribution, say, B2S penguin or B2U box, especially for B2S penguin. So any kind of the enhancement from the theoretical prediction would be the indicator that there is a new component coming to the penguin's loop. And also, this kind of the decays are useful to study the property of the weak interaction in the quark sector, thanks to the complicated decay amplitude and the interference from those amplitude. And also, in addition to this, another special feature we're interested in is in a localized CPU violation. So this is multi-body decay, so we can expand everything into a phase space. So if we can see the additional phase difference between the tree and the penguin interference, then this kind of the thing will be interpreted as a CPU violation localized in a region of the phase space. So basically, this is something we are interested in from the point of view of the experimental side. And our result can be the inputs to the theoretical calculation, which is usually difficult and usually based on the factorization measurement for this kind of the multi-hadronic decay. And regarding the challenge in the experimental measurement, we have to consider the large combinatorial background from the continuous EE to QQ process because all the final states are hadronic. So due to the same hadronic final state from the continuous process, and also it is very difficult to distinguish. So this is basically a statistic problem that we have large amount of the background from this kind of a continuous process. And as we mentioned, for this kind of the multi-body hadronic decay, we are interested to see the structure within the decay. For instance, the decay amplitudes, the spin of the different amplitudes resonance particle, and the interference in between. So how can we see this kind of the feature? We usually utilize a special tool called the Dalitz plot. It is a method to unfold the three-body decay phase space visually. So let me give an example. For instance, if we have three particles, B21, 2, 3, and one of the representation of this Dalitz plot is that the invariant mass of the N12 square versus N13 square. So this N square versus N square will be shown as a triangle. So this triangle is basically the kinematic boundary of the three bodies decay. So everything, this kind of the structure, amplitude, spin, and the interference can be clearly seen. So the left plot is one of the famous example of the BP bar to 3pi0 decay by a crystal ball experiment. So as you can see within this kinematic boundary, everything say the flat one is due to the non-resonance decay, and also the red one, which is the picking structure coming from the different unflavored resonance, they say F2 or F0, something like this. And another example which is related to the topic today is the B23 charged pion performed by LSCB. So you can see this triangle is a little bit from different this one, right? So this border and this border are very close to here, the axis, right? But this one we have a basic empty region here because the final state are identical. So they have identical particle in the final state. So the Dalitz plot triangle can be folded into half of it, but we can still see the expected behavior. So you can see there's a band here, right? And there are two clusters, which means this is a spin one particle. So different band here, if we project the distribution into this x-axis dimension, then we can see different picking structure here, right? So this is how we can see the different decay amplitude and then the spin and also the interference in between, yeah. And next thing is the topic today. So this report includes the study on the two different decay modes. First one is the B02 K show K pi. It was first measured by Babar in which they found a hint of the structure in NK-pi and also asymmetry helicity angle distribution at the low NKK region. And there's a similar measurement published by Belle recently, B2 KEKB decay, in which they found the evidence of a localized evaporation at the low NKK region. So due to this previous measurement, this kind of the special feature, we just try to remeasure this B2 K show KPI to update it to see if there's a new thing can be found in this study. And the second topic, which is the preliminary result, and there's already preprint can be seen now, is the B plus to pi plus pi zero pi zero. So as you can see in the final state, we have two neutral pions. So technically, it's very difficult to handle in our measurement. The first inclusive measurement was performed by Khalil. They set the upper limit to be about 8.9 times 10 to the minus 4. And if we consider a similar decay, B plus to 3 charged pion performed by both Babar and LACB. So both of these experiments performed the 4 amplitude analysis, and they found a very rich structure in this final state and also localized evaluation. And for this pi plus pi zero final state, in our study, of course, we need to consider what is the expected component within this final state. So the majority of this decay is expected to be coming from the B to rho plus pi zero decay, which is about 10 times 10 to minus 6. So it is expected to be roughly 70% of this decay more. So we have to consider this point in our Monte Carlo modeling. Yeah. So this measurement has been measured by both Belle and Babar. And also, as we say, B to rho plus pi zero is expected to be majority, roughly 70%. And there should be some other kind of the sub-decay mode individually, right? And different results from the different sub-decay within this mode are also helpful to determine the CK matrix element. So this mode, we have B to rho plus pi zero, right? If we also combine the result from other rho pi form, which are from other B to 3 pion result, so the combined results are helpful to determine the phi 2, which means alpha. And also the result of the B2 chi C0 pi, where chi C0 will decay to pi pi. So the chi C0 pi's interference and to the non-resonance decay could be also helpful to determine the phi 3, which means gamma. And this is the introduction to the KEKB collider. This is a asymmetric energy E plus E minus collider AKK, where the energy of E plus is 3.5 GeV, energy of E minus is 8 GeV, and the quartz angle is about 11 milliradians. So this setup will be actually different from the new accelerator Super KEKB for the Belle 2 experiment. And the target production process for this collision is E plus E minus to Yun-Tsung Lai to BB bar production, where we use this kind of the data for the B physics measurements, also one of the most important point of the Belle as a B factory. And you can see in this figure is the energy scan of the Yun-Tsung resonance, right? So at the Yun-Tsung 4S on resonance collision, the main background for the BBD has started would be the EE to QQ bar continuum process, where Q equals to UDSC with roughly 3 times larger cross section around this region. So Belle 1 and the KEKB collision have finished their operation in 2008. So they have collected in total about 1 inverse autobahn of the data. About 70% of them, about 700 inverse autobahn are for the Yun-Tsung forest, which correspond to about 700 million of the BB bar pair. So we have used this kind of a large data set for BB bar for any kind of the B physics study. And this is the cut view of the Belle detector. As you can see, it consists of lots of the different several sub-detectors, right? So it's based on the general purpose design with multiple sub-detectors, such that almost all kinds of the decay product from the B or from other particle can be captured by this kind of the general design of detector. Of course, there's something we cannot reach, say the neutrino or the neutron cannot be detected by this design. But anyway, the detail of each subdetector will be mentioned later, along with how we reconstruct our signal B candidate. Okay, so let me move to the analysis strategy and the technical part. So first, in Belle, most of our study are called the blinded analysis, which means we didn't look at the data from the beginning, but we try to use the Monte Carlo simulation for both signal and background. And then we try to construct a pseudo data sample by using those simulated sample for pre-study. After we fully confirm our study and our analysis strategy, and then we look at the data to give the final measurement. So this is called the variety analysis. So first, for signal, how can we simulate and get the quantitative information using Monte Carlo? So we need to assume a branching fraction for our decay. So our target is the Charmless variable decay, right? So the branching fraction will be around the order of 10 to minus 5. And also we have the signal Monte Carlo sample. We can apply different kind of select criteria such that the signal efficiency will be lost step by step. So we can obtain the total reconstruction efficiency by using Monte Carlo sample. So combine this assumed branching fraction and this efficiency from Monte Carlo. This is how we can calculate the expected number of events in the data. Yeah. So that's how we can get this information, and we can construct this so-called pseudo data using everything from Monte Carlo. And this is the event sample categories expected to be seen in the Belle 1 data for business study. So we expect to see signal. So one of the B will decay to our signal process, while the other one of the B will decay randomly. So the definition of this randomly will be defined later. And also we have a continuum background EE to QQ process. And also for the BB bar background, where both of the B will decay randomly. So we expected to see all of this thing in our data. So we need to generate Monte Carlo for all of them to understand them. Then we can understand what we are expected to be seen in the data, right? And the next thing, this is a detailed view about this kind of the Monte Carlo categorization. First, let me talk about signal. So as we say, one of the B will decay to our signal. The other one of the B will decay randomly, right? And when we are trying to pick up those particles to reconstruct our B, of course, there will be a chance that we pick out the correct 3 particle to get the correct B. That's fine. That's what we call the true event. But there's still possibility that we pick out the wrong particle from the other B into our signal B candidate. This kind of the wrongly reconstructed background is called the Silk fit. So this is the first type of the background within the signal sample we need to consider. And then for the BB bar background, as we say, both B will decay randomly in our Monte Carlo configuration. And then this is the detail. First time, if we consider both of a B decay with the B quark to Chang decay process, we call it the generic BB bar process. So usually B to Chang will have larger branching fraction, and most of them have been well measured. And another case is called the B to UDS, the rare decay. So this kind of the branching fraction will be much smaller than the B to Chang process, usually less than 10 to minus 5. And some of them in our Monte Carlo are actually assumed. So maybe there is no this kind of a decay, but we just assume it because physically possible. So this kind of assumed branching fraction is also helpful for us to determine that any kind of a rare decay background coming from will fit into the signal in our study. So this is everything we are expecting to see in our pseudo data sample. So we use this study to construct everything using Monte Carlo and try to understand everything before looking into data. Okay, so this is about the signal reconstruction. So we have the B to K show K pi and B to pi plus pi 0 decay. And then we'll try to pick up those final state particles, which are determined using the detector information. So what we have in the Belle data, we have the charged particle and the neutral particle. For the charged particle, we need to use the tracking device, say the silicon in the innermost one and the drip chamber outside of the silicon. So the silicon detector, usually it is relatively expensive. So we put it in the innermost point to provide the best precision of the tracking and also the vertex purpose. So after we get the track of the charged particle, we get some kinematic information, right? But we still need some further information to determine who it is. This is called the particle identification, PID. So the most difficult part in this PID technique is the separation between K-ion and the pi-ion, because the mass are very close to each other and they are both hadron. So usually we utilize the time-of-flight counter and also aerogel Cherenkov counter, especially this Cherenkov technique is widely used in different experiments for the K-pi suppression. And for the electron, usually the electron and the photon will left most of the energy on the electromagnetic calorimeter. So we use the CSI crystal for the Belle 1 case. So for this large energy cluster, if there is no track associated to it, it is photon. If there's a track, then it is electron. Yeah. And the mu1, we rely on the outermost mu1 and the K-long chamber. And for each mass hypothesis, we have the likelihood value calculated using the detector information for each hypothesis. So we can based on it, we can determine this type of particle is who by using this kind of likelihood value. Yeah. So the neutral particle, as we mentioned, photon is using the calorimeter information. Pi zero, which will decay to 2 photons, is basically a combination of 2 individual clusters in a calorimeter. So we also have the K-long using the outermost chamber, and also the K short to pi. Something like this, we require information from 2 track. Yeah. So this is how we can obtain the final state particle information using the Belle detector. And this is how we can reconstruct our signal B. So we need to pick up the K short K pi, or the pi, 1 charged pion, 2 neutral pion to reconstruct our B candidate. So for the charged particle K and the pi, as we say, we use the tracking device and the PID device. So this kind of the tracking, after we obtain the entire trajectory, we'll expect that this track is coming from very near to the interaction point IP. So we have the requirement on this kind of impact parameter, which means the distance of the track to IP. Once if the track has a large impact parameter, which means it is not originated from IP. Usually this kind of the track is coming from long lifetime particle or from bin background, which is not from B. Yeah. So we also use the likelihood value to distinguish between K-long and pion. For K short to 2 pion decay, so we need to reconstruct 2 charged pion into 1 K short candidate. And this kind of the scheme, we also utilize the neutral based on the neural network to perform multivariate analysis. So a lot of the information are combined here, say the decay length and the pattern of the hits in the inner silicon detector, etc., to enhance the power of the K short reconstruction. And also we have the form momentum of the 2 pion into the form momentum of the K short, right? So for those momentums, we have the vertex constraint fit on them to increase the purity of the reconstruction. In this kind of a reconstruction, we will have this invariant mass distribution for 2 particles into 1 particle. So usually we'll have the mass window selection to reduce the flat component, which is the combinatorial background. So similarly for the pi 0 to 2 photon, which are the 2 individual clusters from the calorimeter, we have the mass constraint fit on the form momentum. And also this is the reconstructing mass window for the pi 0. So we also have a similar mass window requirement on this and gamma. So that's how we obtain the final state particle. We pick up them and reconstruct our B. So as we said, there must be chance that some of the particle are wrongly picked from the other B, which is not from our signal B. So there must be this kind of the cell crossfit fake candidate, right? And also due to this, there will be more than 1 B candidate in an event. So we will select the best one using the chi-square from those vertex or the mass constraint kinematic fit. Okay, up to here is how we reconstruct our signal B. And then after our reconstruction, how can we identify the signal B from the other background? We usually utilize these 2 major variables, which are defined in the central momentum frame. So, and also these 2 variables are widely used in most of the B factory or other flavor factory experiment because we have the constraint that the flavor will be produced in pair. So our heavy metal will also produce in pair, that we can utilize this property to define this variable. First one is called the energy difference. So for our reconstructed B, the energy difference between the bin energy. So these 2, the reconstructed B should be the same as the bin energy, right? So signal B should be peaking exactly at 0, okay? And the rest of the background, say the continuum background, there's no B, so it should be continuum, which means flat. And for the other background coming from the B decay candidate, because there are less component or more component, so the delta E will be shifted from 0. Yeah, so you can see how we can distinguish the signal from all kinds of the background. Yeah, and another variable is called the bin energy constraint mass, MBC. So it's basically the invariant mass of the B candidate, but the energy is replaced with the bin energy. So you can see this is the mass for B, right? It is also expected to be peaking at the 5.279, which is the nominal mass of the bin mass. And the continuum background has this kind of a shape. It will reach 0 at the limit, right? So this is the reason we use this bin energy constraint mass. So this definition was first introduced by the August experiment for this kind of the flavor factory production. So by using this, the continuum background will reach 0, such that we can use a special function also from the Agar's experiment to model it. So it will usually have the shape like this. Yeah. So this is the two major variable for our signal B identification in Belle or say in the B factory. And the first type of the background is the continuum background. As we say, continuum background is flat, right? So it is not a kind of a distinguishment property. It would be relatively a statistical property in our distinguishment. So it would be the dominant source, especially for our hadronic final state. The final state is very difficult to be distinguished. And the major difference is the decay shape between the BB bar and QQ bar. So in the BB bar production, the mass of the B meson is very close to the bin energy. So after the production of a B, they will have a very small momentum. So the final state particle will distribute spherically in the phase space. While for the B to QQ bar, the mass of both of the quark UDSC will have smaller mass than the expected bin momentum. So these two quarks will have a relatively high energy jet, and the final state will also distribute in this kind of a two jet-like. Based on this kind of the shape difference, so we will use the multivariate analysis to combine several different event topology variables. So you can see this is the output if we use the feature discriminants, very powerful to distinguish, right? But we will further combine this feature with 3 more variables, say the flight direction of the B, the flavor taking, and the angle of the thrust axis with the neural network package. So this is the final output. So we can see this is very powerful to reduce the continuum background while keeping most of the signal. And another way to utilize this one is that this kind of the 2 peaks shape can be transformed into this. So it will be both Gaussian-like shape. So the benefit of this transformation is that this distribution will be much easier to model or to the fit. So we have one more additional variable in addition to this delta E and ABC could be utilized in our final fit purpose. Yeah. And next, for the BB bar background, it is different from the previous continuum process. As we said, continuum process is flat and it is statistical issue. But for the BB bar background, usually we need to find out what kind of the B will come into as a peak in our delta E and ABC. So it is, if the peak is very close to our signal peak, then it will be the big trouble. So the way we handle it is that we see if we see the peak in delta E and ABC, we'll find out which mode it is, and we'll project to their original 2-body mass distribution. For instance, B to pi plus pi 0, pi 0, the peaking structure might be from pi 0, pi 0, right? Or might be from pi 0, pi plus. So if the case that D decay to 2 pi 0, this 2 particle will have a peaking structure here. And then we'll just have a mass window around here, say 3 sigma of the resolution, reject everything with this window, such that this peaking background will be totally killed. So this is how we handle the peaking background by using this mass window veto. And also another one is the K-show to pi 0 for the Dalitz decay mode. And another decay mode, B2 K-show K pi, we found actually 7 kind of these cases, which cause the peak in our major signal region. So for all of them, also we make a window and kill the candidate within this Windows region. Yeah. So up to here, we finished the study of all kinds of the signal and the background Monte Carlo, right? The purpose is to understand the behavior of them and also their expected number in the data. So up to here, with signal, we already have enough knowledge in the signal and all kinds of the possible background. And the next step, we are going to extract the signal from the data using the extended unbinned likelihood fit. So by doing this fit on the data, then we can obtain a number of the signal. So which can be used to calculate the inclusive branching fraction for the decay mode. As you can see here, we have the fitting number of signal divided by the reconstruction efficiency from Monte Carlo and the total number of a BB bar in the Belle experiment. And then we can calculate the branching fraction or say the production rate of this decay modes. And also this kind of the fit, we can get signal here, right? If we can do this fit by separating the case for the B plus in the B minus to obtain the EO for these 2 cases separately, then we can get the asymmetry between them, which is ACP, which means CP violation for this decay mode. Yeah. So this is the thing we can obtain inclusively for the decay mode using the unbinned likelihood fit. So practically speaking, in both of the study, we perform the 3D filter on delta E, MBC, and the continuous suppression. So these 3 dimensions, as we shown before, they are the most distinctive variable to distinguish signal from all types of the background. And as in our study, we know that we have the signal and we have continuous background and different baby bar background for each respective component. And then we will define their proportionality density function, PDF, based on the Monte Carlo distribution for the 3 dimensions. So this is the demonstration plot for the 3 major dimensions, delta E, MBC, and the continuous suppression for all types of the component. The red one is the signal. So all the 3-dimensional signal is a peak in the expected region. For the blue one, continuous background, it is flat and also different from the signal. And for the BB bar background, usually they will have peak in some of the dimension, but not exactly the same as the signal. For example, here, we have 2 kind of the B background from B to K shore KK and the pi pi K shore. So they also have the peak in delta E, but in the shifted region. But in other dimension, they look quite similar to signal, right? But in this case, one of the dimension delta E, they have the shifted region, so it will not affect our signal fit result. Yeah. And this is how we model those Monte Carlo samples. So we expect to see all of these components in the data. So for each of them, we use the Monte Carlo sample and model them by using different functions. In general, we will tend to use the analytical function, say the signal for the K shore K pi basically are all Gaussian, some of the different Gaussian functions in the 3 dimensions. But maybe you can notice that there is something called a 2D smooth histogram, right? So why we need to use this special function? For delta E, MBC, and the continuous suppression, when 2 of the dimensions are correlated to each other, then we cannot model their function for each dimension separately. They have to model together because they are correlated to each other. For instance, this is the signal of the B2 pi 0, pi 0. So you can see we make a cut on the delta E region and project to MBC. You can see the shape are different, right? If 2 dimensions are totally uncorrelated, no matter how we select the delta region to project to MBC, the distribution should be exactly the same as shown here. This is QQ case. So if we see this kind of a correlation, these 2 dimensions have to be modeled together using this 2D smooth histogram. So that's the reason. And you might wonder why this K shore K pi is fine, but pi 0 signal we need to use to this smooth histogram is due to this pi 0 reconstruction using the calorimeter. Calorimeter based on the crystal determination, we have the shower leakage problem. So if you go back to that page, the signal peak for the K shore K pi is a very pure peak with good resolution, right? But for the pi 0, there's a long tail left side. It's basically due to the shower leakage. The photon energy detection cannot be done perfectly due to this leakage on the crystal detection. So that would be also the reason why we can see this kind of correlation in the energy related dimension. And this is example. So the black arrow bar are the signal. And this is how we use different function to model our Monte Carlo distribution. As we say, these 2 delta D and MBC are 2D smooth histogram, which basically just how Monte Carlo look like. We make it into the function directly. Let's call the histogram function. And the continuous suppression is the combination of different Gaussian function. For the QQ bar for this decay mode, this is the first order of polynomial. This is a function from arcs, as we mentioned above. And also this is also the Gaussian function for the continuous suppression. And this is the example of one single fit on the Monte Carlo cocktail sample. The red one here is the signal. So as you can see, the picking part in the expected region can be correctly modeled by our signal. And especially for this case, K shore K pi, we expect to see 2 picking background here, right? But our filter can still correctly see this kind of the discrimination between these 3 different picking components, and the signal one can be correctly measured. Yeah, and this is the case for the B2 pi plus pi 0, pi 0. And also, this kind of the data fit on the entire sample can be also done by separating the cases for the B plus and the B minus cases. So by doing this fit separately for the 2 chart case and simultaneously, we can get an yield for these 2 cases and also the asymmetry between them, which is the CP population of this decay. Yeah. So basically, up to here is everything we can do by using this data fit on the inclusive decay mode. And the next thing, as we say, this is three-body Charmless decay mode, right? Three-body, multi-body. So we are interested in the inner structure of this decay mode. Previously, as we say, the 3D unbin likelihood fit on the data, we can get the number of the signal yield. So it is just a number, which means the area of the PDF. Yeah, but it is data, right? So we can never know which event is signal, which event is the background. But as we say, in such kind of the decay, we would like to study the structure in, say, n pi pi or in the Dalitz plot, which means n pi pi squared. In this dimension, which are extra dimension from our filter. Filter is the delta E, MBC continuous suppression, right? But this kind of n pi pi are the different dimension from these three major dimensions. How can we isolate the signal on this dimension and project to those dimensions for further study? So this is one simple example to get the signal isolated distribution on n pi pi. So on this dimension, if we can make the binning, say 5 bins, for each bin, we perform the 3D fit. So level how many bins, then we need to do how many times of this 3D fit separately. For each bin, 3D fit will tell us the fitted signal yield here. Then the signal yield for each bins correspond to the signal isolated histogram for n pi pi. So this is a rather brutal force way to obtain the signal isolated information as a histogram. But there are the different technique. We call it the sPlot technique for signal isolation. So we don't need to do this 3D fit so many times. We just need to perform a global fit one time. So after this fit, each event will be assigned with a weight, or say S weight, based on the likelihood fit result. And the sum of the S weight will equal to the total fitted signal yield. So it is kind of the likelihood for each event that how this event is close to be a signal or not. So using this weighting, we can simply obtain the signal isolated histogram in different dimensions. So this is one illustration. If we do the 2D fit on dimension A and the dimension B is here, right? And then after we get this, all of the event here will be assigned with this S weight. And in another dimension C, which is not related to A and B, we make a binning. In each bin of the C, we sum over the weight within this bin. So that's how we can obtain this signal isolated dimension for different dimension. Yeah. Okay, so this is one example using the pi plus pi 0 Monte Carlo cocktail sample. So in this data fit, we get about 1.1 thousand of the signal yield. And then for all of the event here, there will be a S weight calculated, and the sum of the total S weight of all the event will equal to this. Yeah. If we make the binning on the n pi pi, and then make with each bin, we sum over the weight of all the event, then we can get this kind of the signal isolated distribution for all the 3 dimensions. And also you can see that the red one is the result of the sPlot, and the blue one is the signal distribution. Because this is Monte Carlo, we can put a label on it to know who is the signal. So you can see the result of the sPlot and our signal are totally consistent with each other. Yeah. Okay, next page, and let me start to show you the data result for the B2 casual KPI. The 3D fit tells us that we have 500 of the signal yield, and the inclusive branching fraction is 3.6 times 10 to minus 6. And for the B2 pi plus pi 0, which is preliminary result now, we get about 1,000 of the signal yield. And the inclusive branching fraction is 19 times 10 to minus 6. So this is the inclusive measurement result. And then for the B2 casual KPI, we utilize this sPlot to perform signal isolation on the different dimensions. So the first one is the Dalitz plot. This is the NKK, NKK short, and this one is the M pi K short. So as you can see here, there's the cluster around here, which correspond to a peak at NKK at 1.2 GB. So this is the new measurement found by this decay, a new picking structure and 1.2 GB. And if we project this structure here in M pi K, you can also see a similar picking structure as a residue here. So this is something new found by our study. Maybe it's likely to be coming from something like A or A0 or A2, this kind of the unflammable particle. And also we try to separate this sPlot histogram in the case of the charge plus and the charge minus case. And we didn't see the final state asymmetry for this decay mode. The next one this is the bin by bin result just for your reference. So we separate everything into 5 bins, right? So here is the detail of the measurement within these 5 bins. And the next one is the B2 pi plus pi 0 pi 0. Compared with the B2 K show K pi, we have much larger signal yield for this decay mode. So we are able to perform a more detailed study with larger statistics. So we can not only see the histogram of the sPlot distribution, but also we can fit on it to understand the contribution within this decay. So this is a very advanced study for this decay. So this is one of the example of the sPlot. So you can see there's a peak here, right? And then the rest of them is a flat component. In our Monte Carlo sample, we assume that it will be 30% from the phase-space decay, which means non-resonance. And rest of the 70% will be from the rho plus pi 0. So we can see our feature can correctly separate this kind of the rho and the flat non-resonance distribution. And in the real case of the data, we consider all of this possible decay for this pi plus pi 0 pi 0, not only for the rho, but also rho prime and different kind of the unflavored particle, and also Chi-C0 and Chi-C2. So by generating this kind of a Monte Carlo, we get their distribution, and then we will fit on the data simultaneously for all of them. And similarly, this kind of a fit can be done with charge separation. Then we can obtain the CP validation for each of the decay modes. Okay, so this is the final result for the B2 pi plus pi 0 pi 0. First, let me introduce with you this Dalitz plot. So in this Dalitz plot, what did you see? You can see that there is a very small flat component, right? Which means we see the very small contribution from the non-resonance decay. And there are two clusters, right? If we project to M pi 0, there will be a peak. So these two clusters are basically due to this blue component, which is the rho plus pi 0. So as you can see, these are two peaks here, right? Because the rho is spin 1. So spin 1 decay will have this kind of two polarized distribution. So everything for rho plus pi 0 is as expectation for our measurement. And another thing, if you also see here, there's a cluster around here, which corresponds to a peaking structure at the low M pi 0 region. So this peaking structure is likely to be coming from 3 different resonances, say F0 980, F2 1270, and F0 500. So this is a very exciting new result that we found a new multi-resonance contribution in the low M pi 0 region. So for this region, we also found that the combined significance of the measurement is 9.2 sigma. So this is really an observation for this new stuff. Yeah. And also in addition to the decay mode listed here, we also try to measure the F0 1370, Chi-C0 and Chi-C2, but none of them are observed in this decay. Yeah. And as we mentioned, this kind of the 2D fit can be done by separating the two charge case, B minus and the B plus. And first, you can obviously see in this plot that in a 1.4 GeV, which is the this kind of purple PDF, right? There is a very large asymmetry. B minus obviously has a large contribution than the 1 in the B plus, right? So this one corresponds to F2 1270. Yeah. So this is also something new we found in this study. And if we directly see the ACP as a function of the pi 0 mass, then in 1.4 GeV, this bin has a 3.2 sigma significant convergence. So this is another exciting result observed in this study. Yeah. And if we look back to our previous result of the B23 charge pion by Baba and Belle, which they also have this F2 1270, they also found a similar asymmetry in this F2 1270 decay mode. Yeah. So as a confirmation of our measurement. Yeah. So here is a summary of our B2 pi plus pi 0 measurement result. First of all, for the B rho plus pi 0, it is expected. So we just update this result. We also consider the interference effect with the rho prime pi 0 decay. And as we say, we found a new pi 0 structure likely to be coming from these 3 resonances, F0 500, F0 980, and F2 1270. But actually, if you go back to see previous page, these 3 are very close to each other. So we don't have the information of the interference, and also their shape variables have very large variation according to PDG. So based on this kind of the lack of the different information, we decided that we report a combined branching fraction for B2 X pi, where X decay to pi 0. So in the future, if we can have more understanding and perform the full amplitude analysis, we will have a chance to measure the branching fraction and the interference for these 3 separately. Yeah. And here is a summary. we performed a study on the two Charmless three-body bit decays modes and try to measure their increased information, the structure within the phase space by using the sPlot technique. First, for the B2 KEKB, it is motivated to cross-check the result from the different similar decay modes, and we observe a new picking structure at NKK around 1.2 GB. For B2 pi plus pi 0 pi 0, we perform a more detailed study using the 2D beam fit on the sPlot histogram. First, we found a multi-resonance structure at the low and pi 0 region, and among them, we also found a significant localized CPU violation at 1.4 GB of pi 0 pi 0. So basically, that's everything. In near future, if we want to improve this kind of study, we need to carry out the full amplitude analysis to understand everything. To do that, we require a larger data set from Belle 2 with the improved reconstruction for the neutral particles. Yeah. So here is something about the sPlot and the Belle 2, which is still ongoing for this kind of BCC study. So sPlot is upgraded from the original KEKB. We are aiming for more than 30 times of the instantaneous luminosity of the KEKB with the nano beam scheme. So here is the achievement so far. So the peak luminosity is basically the world record, roughly 2 times of the KEKB record. And I think you are interested in the integrated luminosity, roughly 400 inverse photon in total. So roughly very close to the limits of the Belle 1 already. Yeah, so there's still lots of the papers ongoing. So I think you can check the latest result in some of the summer conference with partial of the data. So I think in the winter conference, you are able to see the new result with all of this Belle 2 data after some processing the scheme process. So please stay tuned with us for more results. That's it. Thank you very much.
Thank you, Yun-Tsung. It's very exciting new results on the pi, as well as the K-K. Any questions from the audience?
Can you go to that nice slide that's after this one with the summary of all the physics and stuff?
You mean this one?
No, the final one that you showed.
This one.
Yeah. So where does this measurement fit within that? Like which of these branches does this measurement facilitate?
I think it will be rare bit decay. Yeah.
Okay, but I guess going sort of like going in the opposite direction, like in terms of like new physics, does this enable some measurement of new particles or something? I guess I'm wondering, like, so what's the sort of motivation behind measuring these rare decays beyond just measuring them?
Yeah, so basically the problem is that we want to understand the weak interaction because it has a very complicated, so many sub-decay modes within one inclusive decay, and they have the interference in between that. So that's the general thing we were interested in. We want to understand the decay amplitude and the interference and the localized version here. So I think it would be relatively within the scope of the weak interaction. Yeah, that's the first thing. But if you are talking about the new particle or the new physics, I think Charmless three-body decay can also contribute to this part. So we are trying to see different resonance particle. So most of them are kind of expected unflavored particle, right? But some of the people are using three-body decay to see if there is a new state here, say pentaquark state, or even grouper using this three-body decay. But it is a relatively more advanced study. If we want to study this kind of a new particle, pentaquark or grouper, we have to do not only full amplitude analysis, but also we need to perform a partial wave analysis to understand much more information than amplitude and the phase difference. Yeah. So this will be a more advanced study. I think we need a few years for Belle 2 to study this point. Yeah.
Thank you.
So if you go back that one slide, just to that, yeah. So if I look at a branching ratio, so if I look at the errors there for the inclusive analysis, right, it's plus minus 1.5 and plus minus 1.4. So that means it's systematics limited. Yeah,
the first one is statistic.
Yeah,
and the second one is systematic. Yeah.
So can you improve on the systematics with Belle 2?
I believe so. Yeah, Belle 2 has also that not only we have the larger statistics, but also the software tools are improved. Yeah, so this part should be also supposed to be much reduced. Yeah.
do you know how much it can be improved there to basically?
I can just give just a moment. Yeah, this is everything we have for this one. So let me see. To give my personal opinion, then you can see here, say tracking and then pion identification, right? Those are highly depends on detector and also reconstruction software. And first, I can tell you that the Pi0 identification also had lots of the effort to improve it, including the correlation problem and the large tail we mentioned. So I believe this part first can be further reduced. Yeah. And also the signal PDF, this is something about the modeling or technique of the study by the user. So it's hard to say it will be improved. And another one is, I didn't mention here, is we use the sPlot technique, right?
Yes.
So yeah, and here. Yeah, so we do a straight fit using sPlot to get this distribution, right? But sPlot itself has some kind of the potential bias, especially for this Pi0 decay mode. We actually did lots of the technical effort to make sPlot working for this decay. Yeah. So in the future, if we can have less correlation due to the shallow leakage of the photon, this correlation can be reduced, and then the sPlot bias can be also reduced. So that's another aspect we are expecting in the systematic side. Yeah. But the major, I would say,
there's a number of improvements.
We have it in the Belle 2 Monte Carlo in the physics, but I cannot tell you now. Maybe.
Yeah. No worries about the. So you expect, okay. So Belle will get a factor of 10. Belle 2 will get a factor of 10 more data, right? So it's so that will bring down the statistical error. I guess get a factor 3.
Yeah, actually, in total, we're expecting, say, 40 or 50 times of the Belle.
Oh, 40 or 50 times. Okay, sorry, my bad. Yeah. Okay, so the challenge will be then to get the systematics down at the same level, right? As the.
Yeah, then I will say we can have something like 30% of the reduction on the systematic. I think, yeah, for most of the study, they claim that for different package, they can reach about a 70% improvement. Yeah, 50% might be too much. Yeah.
Okay, now that's good. That's good. Thanks.
Thank you. Any more questions? In fact, Yun-Tsung, I have one. Just can you go back to the K-short, K-pi, that part? So you also measured the ACP here, but the ACP using the result from the favorite tagging. But you also,
actually, this is not ACP. This is called final state asymmetry. Yeah, we don't exactly use the favorite tagging to do ACP because this is neutral B. Yeah, because we consider that for the statistic, it is not so enough. And if we consider favorite tagging, there will be a dilution factor. So there will be very small amount of the data if we use the favorite tagging. So instead, we try to measure this final state asymmetry. Yeah, of course, in the future, we need to do the real ACP by using the favorite tagging. Yeah.
Okay. Because I thought you're using the favorite tagging information here, but I remember you also used that for your continuum. So I was just wondering that if that would bias your result, but if you just use the final state one, it should be fine. Yeah. Okay, thank you. Any more questions to Yun-Tsung? If not, let's thank Yun-Tsung again